the polynomial functions. And first thing I want you to do is I want you to be very sure that you're comfortable with the definition. Okay, a polynomial function is very, very specific. It's a bunch of terms connected by addition and subtraction, and the terms have to be terms where the x's have exponents that are non-negative integers. Okay, so all the exponents on the x's, or whatever the independent variable is, so the exponents on the variables have to be non-negative integers. So you can't have fractional exponents, you can't have negative exponents. The coefficients can be anything they want to be. They can be any real number, they can be messy, they can be pretty. The cool thing about a polynomial function is that the domain is all real numbers, which means you can plug in any x value you want, and it has a very nice way of graphing, and that's what we're going to look at, is different ways that we can analyze the function to know what its graph is going to look like. But before we do that, let's take a look at these 6 examples and make sure we can identify what's a polynomial and what's not. Look at A. See how with A, if you look at all of the exponents, they're all just pretty little real positive numbers, understood to be an exponent of 1 on that x. So A is a polynomial. How about B? Okay. B is not a polynomial because it's got that denominator. That's actually a rational function, which is what we're going to talk about in the next section. C is a polynomial that a lot of people miss because we forget that what we could do is we could have a little x to the 0 power sitting beside that, because remember, anything to the 0 power is 1. So 5 times 1 would still be 5. So a constant function is actually a polynomial. It's a baby polynomial. So that's definitely a yes. That's a check. Here, my dog, she's going to contribute to our recording. D, that's also a polynomial. How about E? See how we've got that exponent right there of a -1? That's what you're looking for. That's not a non-negative integer. It is most definitely a negative integer, so this is not a function. It's not a polynomial function. Okay, and let's see, what about H? Well, all the exponents look cool. There's a 3, there's a 2, that's understood to be a 1, and yeah, the coefficients are fractions, but that's okay. It says the coefficients can be any old real number. It's the exponents that we're worried about, so that's a yes as well. So, remember how when we were talking about polynomials, when we were talking about quadratics, every time we would look at like the graph and something like f of x equals x squared, and we would say, okay, what does it look like? And we said it looks like a U, and it opens up. And then we said, well, if we put a negative in front of that x squared, what does that do to our function? Well, it flips it upside down, and it looks like a U that's upside down. Well, it turns out that all polynomials that have an even degree are going to act very much like this. So if you look down here at this one and this one, for functions with an even degree and a positive leading coefficient, you're guaranteed that they're going to do something very similar to that x squared graph. They're going to start high, they're going to do some stuff, and they're going to end high. They might go up and down, we don't know, but what we do know is that they are definitely going to start and end high if the leading coefficient is positive. If the leading coefficient is negative, it's going to behave just like a parabola that was turned upside down. Again, I don't know what it's going to do in the middle, but I am guaranteed that if it's an even degree and a negative leading coefficient, I know what's going to happen on the very end. It's going to start low and it's going to end high. So if you look at a polynomial and you look at its degree, remember the degree is the highest power on x. If you look at its degree and it's even and it's a positive leading coefficient, it's going to open up. If it's an even degree and a negative leading coefficient, it's going to open down. Okay. Also, if you'll think for a second, let's switch colors. Think about the base graph of x cubed. That's a good example for us to look at for an odd power. Okay, remember what it looked like? It looked like this. And then we said, well, if we made a negative coefficient, then that flips it right upside down. Looks like this. So we're going to kind of think about all polynomial functions with an odd degree in the same way. So functions that have an odd degree and a positive leading coefficient are going to start low, do something, and end by going high. Oh, sorry. Or if it's got an odd degree and a negative leading coefficient, it's going to start high, do some stuff, and end low. Okay? Now again, we don't know what it's going to do in the middle. We just know what the end behavior is going to be. Okay? And I do want you to pay really close attention to the notation here. They're going to get really more precise with how they use the notation that you're going to be using as you go into calculus. So look at this. As the x's approach negative infinity, that's how you read that. As the x's approach negative infinity, f of x approaches negative infinity. Well, what does that mean? That just means that if you trace the x's to the left, because remember, x's go left and right. So if you trace your function, and you trace your function to the left, which direction do your y values go? Your y values go down. So this is the fancy mathematical way to say that as the x values get really small, the y values get really small as well. As the x's get really big, meaning if you trace the graph to the right, which way do the y's go? Well, the y's go up. They get really big as well. As the x's go toward positive infinity, the y values go toward positive infinity too. Here, as the x's go toward negative infinity, the y values are getting bigger. If you trace the graph to the left, the y values are going up. So as the x's get littler, the y's get bigger. As the x's get bigger, the y's get smaller. As you trace the graph to the right, the y's get smaller. Remember, going to the left means that your x's get smaller. Going to the right means that your x's get bigger. Going up is the y's getting bigger, and going down is the y's getting smaller. Same thing happens down here when you've got your even functions. As the x's go toward negative infinity, the y's go toward positive infinity. As the x's go toward positive infinity, the y's go toward positive infinity. As the x's go to the right, the y's go up. The y's get bigger. And here, as the x's go toward negative infinity, the y's go toward negative infinity. As you go to the left, you also go down. As the x's go to infinity, the y's go to negative infinity. As the x's go up, the y's go down. Okay? All right, now the idea of turning points. Now this is really cool because we can kind of go both ways. If we have a function and we look at its degree, then we know that on the graph, it's going to have at most n minus 1 turning points. Now a turning point is just a place where it turns around. Like you're chasing it from left to right, it's going up, it goes down. It's going down, it goes up. That's all it is for a turning point. It's just the maxes and the mins. Okay? So if I know the degree, for instance, suppose I know the degree is 15, then I know that the function is going to have at most 14 turning points. Now it might have 13 or 12 or 10 or 5 or something less. We don't know. But what we do know is if the degree is 15, it can have at most 14. Okay? We can also go the other way. If we have a graph and we can look at it and we can count the turning points and we see that it's got n minus 1 turning points, then we know it's going to have a degree that's at least one more. So if, for instance, it has 5 turning points, we are guaranteed then that the degree is going to be at least 6. Okay, so I hope that makes sense. We're going to put all this together in terms of how to graph our functions in a minute. Okay. All right, now we're going to throw around some terms and we're going to kind of use them interchangeably. I want to make sure that you're comfortable with that. So this box is what that's for. If you have a function and I tell you that r is a real number for which f of r equals 0, then r is called a real 0 of f. Now we've been doing this all along. Every time we've set the function equal to 0 and we've found the x values where the function equals 0, we've known those are the x-intercepts. Okay, we're just going to be a little more careful now. We're also going to use the term real 0 of a polynomial function is another way we could say it. If we know that r is an x-intercept, then we know that x minus r is a factor. That's the little factor where it came from. And we can also say that r is a solution to the equation of f of x equals 0. And we know all these things. We've been using especially 2, 3, and 4 right along. The one that's new is the first one, but we're going to use this kind of interchangeably, so make sure that you're comfortable with all of them. Okay, have you heard the word multiplicity before? It just means the number of times you get, in this case, the zeros. All right, so what you're going to find is that, you know how like when we were factoring, like suppose we were factoring, x squared plus 4x plus 4. Okay, and that factors into what? X plus 2, or x plus 2 squared. So we know that if we set that equal to 0, we know that we get negative 2 as an x-intercept. And that exponent tells us, well, we actually get that twice. So if we can look at the exponents on the zeros and figure out how many times we get a specific x-intercept, a specific 0, then we know what the graph is going to do around that x-intercept. So in the pages before, we were just looking at what do you do at the end of the behavior. What's it doing now as it goes off to negative infinity or positive infinity with the x's? What's the y's doing? But now here's another way to go in and look at what's it doing there in the middle. I can find my x-intercepts, and now if I can figure out what the multiplicity is for each x-intercept, how many times do I get it, then I can say exactly what the graph is going to do. For instance here, if I get it r as my x-intercept, and I get it twice, then I am guaranteed that the graph cannot cross the will not cross the x-axis at that x-intercept. It's going to bounce. It's going to touch. So it's either going to go like that, or it could come from the bottom and go that way. Okay? But it does not change from one side to the other. If I have a 0, an x-intercept, that I only get once, or 3 times, or 5 times, then what I'm guaranteed is that that x-intercept, the graph is going to cross the x-axis. It's either going to go from the bottom and go up, or it's going to go from the top and go down. Okay. Now, be really careful when we talk about the multiplicity being even or odd. We're not talking about the root itself. We're not talking about whether negative 2 is even or odd. We're talking about the multiplicity, the number of times we get it. Is that number even or odd? Okay. And this just kind of sums it up a little bit more for you. So if C is a real 0 with a multiplicity of m, well, if C is an x-intercept, then I know it comes from the factor x minus c. M tells me the number of times I get it, so it makes sense that that would be the exponent. And C is an x-intercept on the graph. Well, if the multiplicity is even, then the graph is going to touch the x-axis at that point. If m is odd, then it's going to cross the x-axis at that point. So if we have the end behavior, we can find the x-intercepts, and we know their multiplicity, we can sketch the graph very quickly. Okay? All right, so let's just look at a cute little picture to start. Let's see. Turning points. There's a turning point. There's a turning point. There's a turning point. There's a turning point. It just means if you're tracing it, it's a place where your finger turns from going up to going down or going down to going up. Okay? So if it's got 4 turning points, what's the degree going to have to be? Okay, so there's 4 turning points. So the degree is at least 4 plus 1 or 5. Now it might be bigger, but we can look at the x-intercepts here, 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 here. And we can look at what the graph does, and we can kind of know what the multiplicity is going to be. See how here it crosses the x-axis at this x-intercept? That means the multiplicity of that x-intercept must be odd. It might be 1, it might be 3, it might be 5. Same deal here, it crosses. Same deal here, it crosses. Here, it bounces. So that's going to be an even multiplicity, 2, 4, 6. Usually we go with the smallest numbers. The straighter it goes through for the odd multiplicities, the closer it is to 1 for that multiplicity. And we're going to do a couple of examples. Right, so look at this one. Suppose I want to know whether this is an even or odd degree. I think back to my graph of x squared. I think back to my graph of x cubed. And I look at this thing and I see, okay, well, it starts high and it ends low. So it starts and ends in different places, so I know that means it's going to have to be odd. Just that short and sweet. Okay. If I want to do the turning points, I trace it, and anywhere my finger turns around, at one of the maxes or mins, that's a turning point. This one has 2 turning points. So that means my degree is going to be a minimum of 3. Might be higher, but it must be at least 3. Okay. Think about whether the leading coefficient is positive or negative. Okay. If it starts high and it ends low, think about your graph of x cubed. Okay, normally it starts low and ends high, so to get it to start high and end low, I've got to have a negative leading coefficient. So we know that. So see how we're just kind of pulling this stuff off of the pictures? Okay. Now for the zeros and their multiplicity, let's see. Negative 2 is an x-intercept. Let's see. Negative 2 is an x-intercept. And the graph crosses there, so the multiplicity must be odd. 1 is an x-intercept. It crosses, the multiplicity must be odd. And 2 is an x-intercept. And again, the multiplicity must be odd. And how do I know that? Because it crosses. Now, it could be any odd number. It could be 1, it could be 3, it could be 5. You know, when I get ready to write the equation, if negative 2 is an x-intercept, it came from the factor x plus 2. If 1 is an x-intercept, it came from the factor x minus 1. And if 2 is an x-intercept, it came from the factor x minus 2. They have to have odd exponents. I'm going with 1s because that's the simplest. Could be 3, could be 5, but honestly these go through pretty straight, and most of the time when it goes through straight like this, the exponent's going to be 1. You'll notice in the directions that it'll give you the opportunity to have different answers for several of these. Okay? Now one thing I do want to find is I want to find this coefficient. Okay, and the way I'm going to do that is I'm going to come over to my graph and I'm going to pick a point that I haven't used yet, and the y-intercept looks beautiful. Okay? So what's that? 0, negative 1. And I'm going to come over and I'm going to plug that into my function so that I can solve for a. All right, so x is 0. All right, so let's see. So negative 1. This is going to be what? 2 times negative 1 times negative 2. So that's negative 1 equals a times positive 4. Divide both sides by 4. A is negative 1/4. Okay. So my final answer for my function as a possible equation, negative 1/4 x plus 2, x minus 1, x minus 2. Right, want to try another? I don't know why this one didn't print the numbers on the coordinates, but we're just going to count by 1. Okay. All right, so let's do the same thing. We want to know whether it's even or odd. To tell whether it's even or odd, we look at where it starts and where it stops. This one starts low. It ends high. If a graph starts and ends in different places, it must be odd. If it starts low and ends high, and we think about what our base graph, that's the easiest one to remember, x cubed, starting low and ending high is what it does with a positive leading coefficient. I'm going down here and circle positive. Go ahead and get those two. For turning points, I see here and here. Again, you're tracing it from left to right. Your finger changes from going up to going down or going down to going up. And whatever the number of turning points, I add 1, and that's the minimum degree. And these just happen to be the same for both of the two problems. That's just a coincidence. Okay. For the zeros and their multiplicity, let's see. 0, and what is that, 3? All right, so x equals 0. What's the multiplicity? Odd, because it crosses the x-axis there. For 3, that multiplicity is even, because it bounces there. Okay, so from that, we go to the equation. We can write x minus 0, x minus 3 as our factors. But now we know that we don't have to write the minus 0 part. And really, we don't have to put the parentheses around the x. So we could do that. Okay? Now, the multiplicity of the x is odd, so a 1 is fine for that exponent. The multiplicity on 3 is even, so this has to be at least a 2. And, I mean, it could be 4, it could be 6, but I like the smaller number, so I'm sticking with the 2. I'm going to do the same thing we did last time, and we're going to solve for that coefficient. And we do that by picking some other point we haven't used. And this point right here looks like a good one. So 4 goes in for the y. And 1 goes in for the x. And let's clean that up. Alright, so that's negative 2 squared. So that's going to be a positive 4. So we've got 4 equals a times 4. Well, a turns out to be 1. Okay. But we checked it just to be sure. So for the final answer for this one, let's see. F of x. Oops. I'm not liking this new program. F of x equals x times x minus 3, quantity squared. Okay. Can you go backwards? If I give you the equation, can you give me a sketch? Now, to get the degree, you technically could multiply this thing all the way out. But for almost every other question, it's easier to do it with it in factored form. So I'm just going to kind of look. If I take x squared and I multiply it times x, that's going to give me an x to the third. And then times that x, it's going to be an x to the fourth. So if I were to multiply this thing all the way out, my leading term is 1x to the fourth. And I don't care what the rest of it is because I'm after the degree. And the degree here would be 4. Leading coefficients are positive 1. So I think, okay, that means it's going to start high and what? End high. Okay. For the zeros, it's already factored for me. So if I set x equal to 0, well, that's 0. X minus 4 equal to 0 gives me 4. And x plus 1 equal to 0 gives me negative 1. So I can pull that right off the graph. I can think about their multiplicity. And here I know exactly what it is. For 0, the multiplicity is 2. For 4, the multiplicity is 1. And for negative 1, the multiplicity is 1. Now, where's that coming from? It's coming from the exponents. For 0, there's a square on that factor. There's an understood 1 here and an understood 1 there. And from just this, I can sketch a graph. Okay? All right, let's see. I've got an x-intercept at 0. I've got 1 at 4. And I've got 1 at negative 1. Okay, now notice I have not put a scale on y because this is just a rough sketch. But what I know that at 0, because the multiplicity is 2, it's going to have to bounce there. So it's either going to go like this, or it's going to go like this, okay? And I'm not sure which yet. And at the other two, because their multiplicities are 1, it's going to have to cross. So how do I know what happens? I go over here and I go back to the top, and I know the end behavior said it was going to start high. Well, if it's going to start high, it's going to go to the first x-intercept, and that's the one with the odd multiplicity, so it's going to have to cross there. Then that means it can't cross back at 0, so it's going to have to bounce. And then it's going to have to cross there to end by going up. See how I did that? I just put together what I knew the end behavior would have to be and what I knew the behavior would have to be at each of the x-intercepts, and I made it all fit together. I did not put a scale on the y because I really don't know how far down these two turning points are. And I don't really, I mean, if I needed to find that, I could plug numbers in and I could check it. But this is a rough sketch that tells me the behavior of the graph, which is mostly what I'm after. Notice for the y-intercept, that's when x is 0. And that 0 squared at the front is going to wipe that whole thing out. So the x and the y-intercept, well, excuse me, the y-intercept is at 0, 0. Now, I wanted to show you, and I purposely picked this one to be very similar. I just moved where the square was. Okay, so if I think, okay, degree means I need to know what would happen if it were all multiplied out. This binomial in the middle, if I multiply that out, that would give me an x squared as the first term, times this x would be an x to the third, times this x would be an x to the fourth. So it does end up being the 1x to the fourth again. Okay, again, it was trying to be kind of similar. So that means this degree is also 4. This behavior, also starting high and ending high. Now, for the zeros, well, x is 0 with a multiplicity of 1. X is 1 with a multiplicity of 2. And x is 2 with a multiplicity of 1. So it's very, very similar. Okay, same deal even with the y-intercept. When you put in 0 for x, you're going to get 0 for y. Okay. To sketch this, all right, let's see. We've got an x-intercept at 0. We've got an x-intercept at 1. We've got an x-intercept at 2. It starts high. It ends high. And let's see. It's going to go through 0, bounce at 1, and up again through 2. All right. Again, I didn't put a scale on y. I don't know how far down it's coming at those turning points. If I care, I could plug in, 0.5 or 1.5, and I could check a point if I needed to. But for right now, this is enough to give me the behavior of the graph.